Welcome back to our studies on canonical ensemble. We have studied, we have an idea about the theoretical basis of canonical ensemble. We formulated the bridging equation connecting the micro world and the macro world as A is equal to minus kT log Q, where Q is the canonical, we call it as the partition function, or we can call it as the canonical partition function. In the canonical partition function, the equation was, the canonical partition function was given by sum over e raised to minus beta ei. Suppose you have one energy E. In this case, you have one particle, and then you can, a large number of states will be available. One particle can have a large number of states, different energy states will be there. Therefore, this partition function gives the idea how to find the partition function. You have to take all the possible energies and sum it up. Instead of that, if I take two particles in the same state, then now you have the total energy is given by only one state is there. Therefore, there is no need for a summation. Your equation will be e raised to minus beta, only one state with the two particles in the same state. Therefore, energy will be e raised to minus beta into 2e, which you have your the expression for exponential e raised to xy. You can write that as e raised to x whole raised to y. Similarly, you can write your e raised to minus beta 2e, which is our partition function, as e raised to minus beta e whole square. And what was our e raised to minus beta e? It was if a single particle was in the state E, if I have a single particle in the state E, and then the partition function will be for Q1. For a one particle will be e raised to minus beta e. If I have two particles, I can write this as Q2, which will be equal to e raised to minus beta 2e. But e raised to minus beta 2e, I can write it as e raised to minus beta e whole square. And e raised to minus beta e was our previous Q1. Therefore, this will become Q1 square. Therefore, I can extend this and say that Qn, if I have n particles having the same energy, then Qn I can write it as Q1 raised to n. This is how, therefore, there is, if you have a large number of particles having the same energy, then you can always write your Qn is equal to, you need to calculate only the single particle partition function, and then you can take the n raised to n and evaluate Qn. Therefore, if you have n particles, your bridging equation will be A is equal to minus kT log Qn, and in this case it will be minus kT log Q1 raised to n, or this same principle, logarithm of x raised to y, you can take it as logarithm of x raised to y, you can write it as y log x. Therefore, your equation now will become minus n kT log q. These are the techniques of evaluating the partition function. If you have large number of particles, n particles, your partition function can be, your Helmholtz free energy can be written as in this form, or basically it will be minus kT log Q1, which can be rewritten as minus nkt log Q1, Therefore, now we will start doing some problems. Evaluating the partition function. What is this equation? What is the problem? Consider a system where three energy levels are 0, epsilon and 2 epsilon. the energy level epsilon is twofold degenerate and others are non-degenerate. The partition function is, what is the equation for the partition function? Therefore, you have that energies are given to be 0, epsilon and 2 epsilon. Energies are given 0, epsilon and 2 epsilon. But the energy level epsilon is twofold degenerated. Therefore, your partition function is given by now G1 e raised to minus beta E1, since 3 states are there, G2 e raised to minus beta E2 plus G3 e raised to minus beta E3. Your G1 is 1 and your G2 is 2 and the G3 is 1. Therefore, this expression will become e raised to minus beta 0 is 1, 1 plus 2 e raised to minus beta epsilon plus e raised to minus 2 beta epsilon, e raised to minus 2 beta epsilon. This is your partition function. But you are in your question, actually such a choice was not given. You have one choice is 1 plus 2 e raised to minus beta epsilon. Second choice was 2 e raised to minus beta epsilon plus e raised to minus 2 beta epsilon. And the third choice was 1 plus e raised to minus beta epsilon whole square. Directly it is not given. That is, your answer was 1 plus 2 e raised to minus beta epsilon plus e raised to minus 2 beta epsilon. And here you have 1 plus 2 e raised to minus beta epsilon plus e raised to minus 2 beta epsilon, which is not given in your. Therefore, what you have now is Q is equal to 1 plus 2 e raised to minus beta epsilon plus e raised to minus 2 beta epsilon. Actually, this you will be able to get in your third choice 1 plus, what was your, I will write e raised to minus beta epsilon whole square. If I take 1 plus e raised to minus beta epsilon whole square, which is equal to something like a plus b whole square, which is equal to a square plus 2ab plus b square. Therefore, your a is 1, therefore 1 plus 2ab, 2 e raised to minus beta epsilon plus b square. B is your e raised to minus beta epsilon whole square, which will be equal to e raised to minus 2 beta epsilon. This is how the question comes. Directly sometimes your answer will not be given, but in an alternate way they had given the answer, which is 1 plus e raised to minus beta epsilon whole square. Now, second problem. An ensemble of quantum harmonic oscillator is kept at a finite temperature T. That means the temperature is constant, which means it is a canonical ensemble. The partition function of a single oscillator with energy levels n plus half h cut omega is given by. You are asked to find out the partition function for a quantum one-dimensional quantum. This is n plus half h cut omega. From this energy value, you have to see that it is one-dimensional harmonic oscillator. Therefore, you have to find out what is the partition function. Therefore, your energy is n plus half h cut omega, and your partition function is given by, now your summation is now not our I, it is our n. Actually, the quantum harmonic oscillator n will be varying from 0 to up to infinity. Therefore, n is equal to 0 to infinity. In the earlier case, I had not given you what is the final value, because final value changes, initial value also changes. For example, instead of this one-dimensional harmonic oscillator, if it is a particle in a box, n will be from 1 to infinity. Therefore, different harmonic oscillators, the value of n will be varying. Therefore, the range of n will be varying. Therefore, this equation is n equal to 0 to infinity e raised to minus beta n plus half h cut omega. Now, the summation is not applicable for this beta half h cut omega. Therefore, I will take that outside, minus beta h cut omega divided by 2 sum over n equal to 0 to infinity e raised to minus beta nh cut omega. Minus beta nh cut. Therefore, your energy was single, that is one dimensional harmonic oscillator with a 1 0-point energy half h cut omega. Now, I have taken the part which does not have that n, and now this summation is our n equal to 0 to infinity e raised to minus beta nh cut omega. Sum over, there is a very famous Taylor series expression, sum over n equal to 0 to infinity x raised to n, which is equal to 1 divided by 1 minus x, 1 divided by 1 minus x. Therefore, to use that equation, I have to rewrite this expression. Therefore, my partition function I can rewrite as e raised to minus beta h cut omega divided by 2 sum over n equal to 0 to infinity. Use the method of the exponential, the power of exponential. E raised to xy, you can write it as e raised to x whole raised to y. Therefore, similar to that, I can write down e raised to minus beta h cut omega. I can take that n outside, and then your x now becomes, x is equal to e raised to minus beta h cut omega. X is now e raised to minus beta h cut omega. Therefore, your q now becomes e raised to minus beta h cut omega by 2 summation over x raised to n, which will be equal to 1 divided by 1 minus x. X is e raised to minus beta h cut omega. Therefore, your partition function can be written as e raised to minus beta h cut omega divided by 2 whole divided by 1 minus e raised to minus beta h cut omega. That is your partition function. In some textbooks, instead of q, they will be using this z also. Z, sometimes your partition function is represented by the earlier books represented the partition function by the letter z. Therefore, z is equal to q e raised to minus beta h cut omega divided by 1 minus e raised to minus beta h cut omega. There is one more way of writing this partition function, but that is what was not given in your choice, but you can remember that. Therefore, you have this partition function q is given by e raised to minus beta h cut omega divided by 2 divided by 1 minus e raised to minus beta h cut omega. I can take that e raised to minus beta h cut omega by 2 to the denominator. Therefore, this becomes e raised to plus beta h cut omega by 2 whole into 1 minus e raised to minus beta h cut omega. If I can take this plus e raised to beta h cut omega by 2 inside the bracket, therefore, first term becomes e raised to beta h cut omega by 2. This is half beta h cut omega, and you have minus 1 beta h cut omega there. Half minus 1 will be equal to minus. Therefore, your expression can be written as 1 divided by e raised to beta h cut omega by 2 minus e raised to minus beta h cut omega by 2. And e raised to x minus e raised to minus x, you can write it as 2 sin hx. Therefore, you can write your partition function also as 2 hyperbolic function sin hx. Your x is now here beta h cut omega by 2. This is also another form of partition function. This is another form of partition function, but in your question, this was the result that was expected. That is, you have the choices are e raised to minus beta h cut omega by 2 divided by 1 minus e raised to minus beta h cut omega, and you have another choice is 1 plus. Another choice is there is no other numerator is not there, 1 minus. Therefore, your answer is the first one, that is e raised to minus beta h cut omega by 2 divided by 1 minus e raised to minus beta h cut omega. Therefore, that was the second problem. Now, we will go for the third problem. Oh yes, this was the way in which you can find out this one. Next is find out the partition function for a system with energies kT and 2 kT. That is a very interesting problem. You are given the energies are the first energy is given by kT and the second energy is given by 2 kT. 2 kT. Therefore, what is your partition function? Partition function is first energy e raised to minus beta E1 plus e raised to minus beta E2. Therefore, beta is 1 divided by kT. Therefore, e raised to minus kT divided by kT, that is e raised to minus 1 plus e raised to minus beta 1 by kT. E2 is 2 kT. Therefore, this is minus 2. This I can rewrite as 1 by E plus 1 by E square, which I can take as the LCM as E square. Therefore, this is E square. This goes E times plus 1. Therefore, 1 plus E divided by E square. 1 plus E divided by E square. This is the expression for the partition function. Therefore, partition function for a system with energies kT and 2 kT is given by 1 plus E divided by E square e raised to 4, 1 plus E divided by E cube, that is 1 plus E divided by e raised to 1, 1 plus E divided by E square. The correct answer is D, 1 plus E divided by E square. This is how your problems will be from the evaluation of the partition function. Therefore, once again I will tell you what is this partition function. Therefore, what we had done is, here in this canonical ensemble you have this bridging equation that was obtained as minus kT log, you have n particles, I can write it as Qn, and Qn is given by sum over I e raised to minus beta Ei. If you have multiple energies with degeneracies, this expression I can write it as Gi e raised to minus beta Ei, where Gi represent the or multiplicity. It can be, if it is a classical system, you can say it is a multiplicity. If it is a quantum energy, this expression can be written as sum over n Gn e raised to minus beta En, where Gn has got a specific, it will be having a particular equation, and that Gn in the case of a harmonic oscillator in 3 dimension, this is the equation that has been multiply asked for the gate examination or UGC examination, that is Gn in 3 dimension will be given by n plus 1 into n plus 2 divided by 2. You will be asked to find out what are the number of degenerated energies for the nth, 3rd level, 4th level, etc. Therefore, Gn e raised to minus beta En. This is how you can evaluate the partition function. And Gn represents either the multiplicity or degeneracy. If it is a quantum system, there will be a specific equation, particular equation for that. If it is a classical equation, it is a classical energy, then sometimes your G will be given to you as numbers. There will be no particular equation for that. It will be given as a number, and then you will have to substitute that. But if it is a quantum, definitely there will be some formula for that. A formula will be there that you have to use and evaluate the partition function. This is how you can. And one more point that I have to tell you is that if you have n particles, then your Qn will be equal to Q1 raised to n. Q1 raised to n. These are the basic ideas in canonical ensemble. We had discussed the details of computing the partition function in this section. We had also defined the n particle partition function, which is given by Q1 raised to n. I had worked out 3 problems. A large number of problems which you can attempt, similar problems will be there. And after these problems, I think you will be able to evaluate if the different energies are given. You can use this method to evaluate the partition function. I hope you can solve the partition function by hearing this section. Okay, thank you.